developed such a wobble is because, and it made such a mess of a picture, is it was not known at the time the amount of differential heating that a spacecraft experiences in space. The shadowed side of the spacecraft is at a temperature of space, which is 4 degrees Kelvin, negative 200 degrees, let's just make it that way. The sunny side of the aircraft is cooking at as much as 70 or 80 degrees Celsius, which is well over 100 degrees Fahrenheit. That kind of, and these parts of the craft are immediately adjacent to each other. And we're not talking about a large object here either. But even modern satellites that are the size of an average school bus are actually being physically twisted in orbit as they're going from night into day. They are physically being twisted out of shape by this difference in the temperatures on the sunny side and on the shadow, and anything in the sun and anything that's in the shadow. So because of this active deformation, plus the atmospheric drag, it was never going to achieve a stable spin. And so we always learn. There's progress, The world's first weather satellite, TIROS-1, was launched in April of 1960. So again, less than a year later, we keep on growing, make our advances, learn our lessons, and it was this this particular satellite, TIROS-1, only lived for about 78 days. We lost it to an electrical failure, but it managed to acquire in that time over 23,000 images that it transmitted to the ground station in Hawaii. There are multiple ground stations actually throughout the globe that these satellites, as they pass over, they dump the data in a very directed, high-speed data stream. And that is, so they store the data on board. When you reach a ground station, they dump as much of it as they can, continue on, next ground station, they do another data dump, and that's just kind of how it's a continuous process like that. The data goes to various data centers, which has been aggregated, passed on to processing centers for processing into various physical quantities, eventually gets fed into weather forecast models, into supercomputers, and then eventually, after all that is done, you see that as a weather forecast map on the universe. But all these systems were, so as this little satellite, TIROS-1, was transmitting its images, these systems that I just described were being actively developed so that when the next one came up and the next one after that, we were ready for the volume of data that they're capable of sending and how quickly they're able to acquire the information. So TIROS-1, this is the first light image, is the first image that it had ever acquired. It is, it did achieve the first long-term observation of a developing weather system. It was never been, everyone had assumed that yes, they develop, but to actually, and folks actually had a pretty decent idea of how they function just from ground observations and from a little bit from aircraft, but it's never been seen from space. It's never been, you've never gotten a true bird's eye view to one of these enormous weather systems that easily, can span the entire continental United States. No big deal. That's average size. And so they were, based on the analysis of these images, meteorologists were able to make a first accurate weather forecast using space-based data. So that was in the year 1960. So Tiro's series didn't stop there. The first series, so the first set of them, there were 10 satellites that were testing various aspects of meteorological research. They each carried a different kind of a test instrument, experimental instrument, to see what could we see, what was possible, what kind of data, because we say, okay, well, physics tells us we ought to be able to see this if we look at it this way. So they would build an experiment, build a detector, load it on one of these little satellites, send it up, see how it works, rinse and repeat. So TIROS 9 was in 1965, was acquired enough data that it was able to actually create the first global weather mosaic image. So this was acquired on February 13th, 1965. It was stitched together out of 450 individual images. To actually get this very first image of what global weather looks like for an entire day. And that was never done before. That, again, even when they were able to take when the satellite, so we got it stabilized, now we can take good pictures, but to actually be able to combine all those, get enough of those pictures that were good, because not everything was good, and get enough of these pictures in a day that the instrumentation had gotten stable enough that to be able to get enough of these images in a day to stitch a global view of what the weather looks like today, right now. That was the first, so TIROS 9 was the first satellite that allowed us to do that. Now, of course, now we take these global satellite images for granted. There's whole websites that you can go to and just see, like, okay, what does the Earth looks like today? What did it look like last week? You can do that, you take it for granted. But at the time, I mean, this was, so that was kind of, ultimate headline news to be able to do that.
In 1965, when they stitched these together, was that a computer-based operation or automatically they were cut and paste?
They were cut and pasted. Yeah. There was not enough computational power in the entire globe to stitch those images on the computer. That was not going to happen. This was actually done by hand. They were printed. The photographs were printed out and actually hand. It was a lot of glue stick and scissors, but it was possible to do. Well, the TIROS program was so successful that the National Oceanic and Atmospheric Administration had made it official, and TIROS got a new name. Instead of television infrared operational satellite, NOAA basically changed all the names and said, okay, now they're going to get an upgrade, and they're going to now be numbered just NOAA and a number. So the first operational And they basically became the standard for space-based weather observations. And so NOAA-1 was launched in December 1970. Next upgrade was NOAA-6 in 1979. And, well, if it ain't broke, don't fix it. They had continued to carry the same instrument, the Advanced Very High Resolution Radiometer, to this day. So this AVHRR, the Advanced Very High Resolution Radiometer, has its claim to fame is over 40 years. It's over 40 years of data, longest continuous satellite instrument data record. EU METSAT METOP platforms, which are European weather satellites, still carry this instrument, alongside other ones, but they still carry this imager just to continue data record. It doesn't take much to put it on a school bus sized platform. You're talking about something that you could carry out of this, a couple of people could carry out of this room easily, and it doesn't take much to operate. It's not a big hit to actually put it up there. It doesn't take a lot of power. So they're just kind of keeping it up there, even though, of course, things have moved on. But in terms of instrumentation advancements, this picture, doesn't have a lot of resolution, but it had just enough that you could use it to do a lot of very useful science. It collected just enough data that you could do something useful with it. So this image from one of AVHR's channels actually is from April 13th of 2023, so just last year. And so somewhere in the, I don't know if I can get I guess I can't get a pointer. We don't have a pointer. Yeah. Well, so somewhere in the far end of this image is the state of Maryland. So that the blue box is where this image fits on planet Earth. Somewhere in there, in the right part of the image where that orange box is the state of Maryland. Can't really make out much of it, but it's one of those things where some information is still better to have than absolutely nothing. Well, yes, if it ain't broke, don't fix it. But at some point, it gets to the point where being set in one's way is not a very good thing. So if there is a race to speak of, it's more the one between NASA and NOAA. We kind of have a minor competition going. So yes, longest continuous data record. But the instrumentation hasn't been updated as the available technologies evolved. NOAA's instrumentation hadn't been updated in 40 years. And at some point, it gets so long in the tooth, well, it might as well be dinosaur. So NASA developed its own observation system, called it the Earth-Obsering system, the EOS. And the big difference between the Earth-Obsering system and NOAA's cute weather satellite was that the NASA's system viewed Earth as a system. We weren't just looking at the weather. the Earth-Observing system was looking at, literally at Earth, and that was with the launch of EOS Terra in December of 1999, it was basically the science of Earth system science came to be. It was not something that was thought of very much before. Is that everybody, okay, well, somebody study over there studying atmosphere, and over there somebody studying hydrosphere, and the biosphere, and the lithosphere, and the cryosphere over there chipping away at the ice cubes. Everybody was in their own way, in their own world, not really talking very much to each other. So viewing the Earth as a system allowed to bridge a lot of these disciplines, providing the instrumentation that facilitated bridging these divides, breaking down the silos, creating really Earth system science research. Looking like, okay, how does the hydrosphere and biosphere affect the atmosphere? How do the different systems of Earth operate, how different spheres of Earth interoperate with each other? And so this set of satellites had allowed us to really start looking at Earth's observation as like, yeah, it's not just about the weather. It's about really everything else that is going on. All of a sudden, we were able to track from a single platform, we're able to track ocean productivity, which immediately then translated into being able to track fishing stocks for commercial fishing. We're able to see from the same platform without having, why it's important to have the same platform is it's really, truly not fun trying to stitch data together, even on the computer, from different instruments that took observations at different times, possibly at different days, and, oh, there were no clouds yesterday, but there are clouds today. You cannot get any of the data to match up. The only constant thing about the planet Earth is it's always changing. Nothing is ever the same. So having the instrumentation on a single platform that is acquiring data that is pre-lined up, so when you get an image from one instrument, it lines up with an image from another instrument. And so it allows you to really kind of do a lot of things with a minimum amount of effort, a lot of science with a minimum amount of effort. And that was the goal of the EOS program. And that goal has been accomplished with extreme success. So I started at Goddard just a few weeks after EOS Aqua was launched. So I've been with the EOS program pretty much just about from the beginning. So I've seen most of these satellites go up, not actually stood there and watched it, but at least saw the launch on NASA TV because they broadcast them. And but I've been involved in one way or another with pretty much all of these missions. And so that was a big. So what kind of difference does it make? So we looked at AVHIR where you could, well, I don't know, if you used a lot of imagination, I mean, maybe you could pretend that some of these dots are the Chesapeake Bay. So this image of the same exact day, taken at the same exact time, from the EOS Aqua, from the imaging instrument on board EOS Aqua. And that right there in the middle is the Deep Creek Lake. So this image is centered on Garrett County, Maryland, and that right there is the lake. And we're right there on the north end of it, we're right here. So pretty big improvement, taking advantage of modern technology is not a bad thing. So the EOS Aqua and its sister EOS Terra were able to acquire data at a resolution as high as 250 meters. So that is less than a quarter of a mile is 1 point. So as you can see, our county and our lake are easily visible from space. So there is a website that you can go to, and you can look at images from the Earth-Obsering system. You know, it updates for any day since for the last 20 years. And that is the URL for that. It's worldview Earth data nasa.gov. It's a public website. Images are free. You can zoom in. You can bring up different, if you're interested. And actually, I find that website is actually very, very useful and very interesting in terms of being able to bring a lot of these kind of things into the classroom. As say you're teaching social science, and you want to see, so the obvious question that arises, okay, we're doing ancient history. Why did Italy unite and grow into the Roman Empire? Why did Greece remain a loose collection of city-states that did more squabbling with each other than cooperating? When you get a satellite image, a high-resolution satellite image of what Italy looks like and what Greece looks like, you see the reason the Greeks always fought with each other is purely geography. Because they were sandwiched into these narrow valleys between the mountains. Isolation breeds distrust. And so and also it's difficult to travel. It's difficult to get from one city to another. So it was easier to spread rumors and squabble with each other than to work together. That is not the case when you look from been up here since 1999. It is thoroughly out of gas. And it is running, it runs out of fuel. We're no longer able to maintain orbit. Pretty much goes into the drink. Aqua's been up there since 2002. Aqua is probably also with the same design expectation of 5 years. It's been able to, it has a little bit more fuel left. It was able to maintain an orbit that required fewer corrections, with time. But they're approaching their end of life. SUMI and BP is still young. So from 2011, that's still considered a young instrument. So we expect to be getting data from it for at least another 5 or 6 years. Never you mind, again, the expected design life is about 5 to 7 years. That is what budgeted for. So when the new satellite is being proposed to Congress, this is what to the program managers. So we have to write in at least 5 years design life. This is what we expect for this many $1 million we're sinking into this. But in reality, what ends up happening is they live on for quite a long time. And I can tell you it's a long time because my car is a 2002. So yeah, it's a long time. There are other research communities that say, yeah, weather satellites, imagery is great, but we're not interested in seeing, we want to look closer. This is not close enough. We want to study biosphere, we want to study biology, we want to do geology, we want to do agriculture, and we want to do drought monitoring, and we don't want the weather satellites. They're not high resolution enough. We want to be able to see individual cornfields, and we want the appropriate. We want our whole other system just for that. So the series of extremely high resolution, small, high resolution satellites that started. So Landsat series started launching since July of 1972. We're up to, that was Landsat 1. We're now on to Landsat 9. And so if we could see, if on the image from EOS Aqua, we could just see our lake. We could discern the shape. Wasn't much. Well, this image that was acquired on a nice clear day from Landsat 9, which is the newest satellite that just went up in 2020, on this past summer, July 28th, was a nice clear day, but you can actually, in this part, you can actually see where Garrett College is. So this is only in this image, this is only the north end of Dickie Cliff. You can see the highway, you can see the bridge across, the lake right there. You can see the college just to the right of the fork. And so Landsat has resolutions as high as to all these. So Sentinel-2 is EUMETSAT, and Iconos and Worldview are commercial. So they produce high-resolution GIS maps. Are these instruments instruments useful for Earth science? You bet they are. That was actually a project that I started a couple of years ago that has turned out to be with Landsat 8 and Landsat 9. Those instruments, they put enough in there, but they actually become useful to do very high resolution atmospheric science research on. And this is a project that I spun up a couple of years ago. It was fun. And that, of course, is still going. Yes?
When it says the resolution is as high as 1-15M, that's one, I'm not sure exactly what that means.
It's between one iconos and worldview can go down as low as high as 1 meter. 1 point in the image, 1 meter. Landsat standard resolution is 15 meters. So this Landsat image, each point is 15 meters. So each point is about 15 yards.
I misunderstood. I thought that the 1-15M was one resolution, but you're saying 1 meter to 15 meters.
Yes.
I get it.
It depends on the satellite.
Got
Because
it.
Iconos, which unfortunately has ceased operations in 2015, that one was able to take images as high as the resolution was as high as 1 meter. So 3 feet per so each point was about 3 feet.
I understand now. Thank you.
Yeah. So this one is so this is a 15-meter image. So each point in this image is 15 meters. So about 45 feet.
Got it. Thank you very much.
Okay. Well, so we have this. So we have the extreme high resolution community. Well, of course, there's always the other side. So the weather satellites kind of sit in the middle with moderate resolution. You have the high resolution crowd with Landsat, Sentinel, and Iconos and Worldview. On the other side, you have, well, that view is too close in. We don't really care too much what the resolution is. We want to see the whole Earth all at once. And so all the high resolution instruments and the weather satellites, they all orbit at about 700 kilometers from, so about 600 miles above Earth. Geostationary satellites orbit at 36,000 kilometers. The orbit is such that they are able to, as they orbit, they always look at the same point on Earth at all times. So the weather kind of ends up moving across their field of view. So it started out with, again, long-running program. The first GOES satellite went up in 1975. The latest GOES satellite went up in 2016. And so it started with, so the first image of Earth acquired by GOES 1 was on October 25th, 1975. This is an image from GOES, and it was not possible to do color imagery because there were only a couple of channels. They were purely for tracking weather systems across very large scale, across very large area. And the images came down until GOES 16, really. The images came down only about once an hour. And a lot of the processing was actually still done by hand. Because, well, if they're only coming once an hour, so you could figure out which way the wind is blowing by comparing the two images and seeing, okay, this cloud moved over here, or this far, okay, well, that's the wind speed and that's the wind direction. There you go. Send it to the forecasters. The GOES 16 and its sister GOES West, GOES 17, produce images of enormous size and all the tracking of features and such is highly automated. And so they're still able to, and they're able to capture now, the GOES 16 and GOES 17 are able to capture information from 36,000 kilometers away at almost the same resolution as the standard weather satellite, which is about 1 kilometer. So technology moves on, and technology, also communication networks have improved, because it would have been absolutely unheard of to transmit that much data. A single GOES image now is 20,000 pixels squared. An image transmitted by GOES 1 is 200 pixels squared. It's a very big difference. And also, so the communications network had to improve. But a lot of those improvements were actually paved by the U.S. system. That when the U.S. satellites launched, it was unprecedented that they transmitted data. They acquired a new image every 5 minutes. It was an absolutely unprecedented data rate. And we did have some early transmission issues where we were losing some of the data. They were not able to dump it quickly enough. But we caught up with them eventually. And so now so we've gone out to 36,000 miles. Well, how about 1 million? And so there is a mission called Discover, the Deep Space Climate Observatory, that does not orbit the Earth. It takes observations of the Earth, but does not orbit the Earth. There are these points, again, mathematical points, in the Earth-Moon-Sun system that allow a body to maintain a stable position if they were to exactly locate at that point. Because it just so happens that all the forces in those specific points, as shown in this chart, happen to cancel. Now the points are mathematical, meaning you can never actually be there, but it is possible to orbit a point like that and maintain a stable location in these kind of very interesting points. So James Webb Space Telescope is at L2. Nice thing about being at L2, the Earth is always blocking the sun out of view. That all these points move together with the Earth as the Earth is orbiting the sun. So if you park yourself at L2, the sun is the stray light from the sun is never going to bother you. You have the best view of deep space. And so James Webb is actually located at L2. Discover looks both ways, and it is located at L1, about 1 million miles away from Earth. And it has some instruments that are facing the sun, and it is able to, this particular satellite is able to detect solar storms and give us some early warnings of solar flares. It also has instruments that point back at Earth. And from its unique observation perspective, so this is an image acquired by Discover on July 23rd, 2023. So the advantage of Discover is that the sun is always in the same place, because the sun is always at Discover's back when it's looking down at Earth, sitting at L1. And so when we solve the various radiation equations to get from the And of course, as a treat, being a million miles away, well, look where the moon is located. You're further away from Earth than the moon is. And so about every 6 months or so, Discover spacecraft treats us to the view of the dark side of the moon as the moon traverses between, so Discover is parked at L1 and it's just sitting there doing its thing, and the moon orbits and passes across the camera's field of view. And so about every 6 months or so, we get to see the side of the moon not visible from, the side of the moon that is never visible from Earth. Now, of course, it's not actually the dark side of the moon because, look, it's nicely lit up, but it's the side of the moon that we never see from Earth. Well, I will leave you with this fresh image taken by US Terra Modus Imager. It's the main imager on the US Terra, one of my favorite satellites. That was acquired this morning at 10, the image of the state of Maryland. That was acquired this morning at about 10 a.m., a little after 10 a.m. And you can see who got snow and who didn't. So, that's all I have. And you guys want to ask any more questions? Feel free. Yes?
I may have this wrong, if I do, I apologize. When we launched the James Webb satellite or the telescope, I believe it was supposed to see the beginning, in other words, it was supposed to see as far as the universe was.
Yes.
And somehow, again, I apologize if I'm wrong about this, it saw a lot more than, in other words, it was supposed to see the end of the universe, like, okay, this is as far as the universe goes, and yet it was seeing more things than past the universe.
Well, it was designed to, basically, it's the same kind of thing as we say that our design life is 5 years.
Okay.
We cross our fingers and hope it lasts that long. When James Webb was built, the instrumentation was designed to see that much closer to the being, at least that far towards the Big Bang. It's at least, it's the minimum. So the fact that we're able to see more, yay bonus. It was basically given a minimum, okay, we expected to at least see this far. We cross our fingers and hop on one foot and hope we're gonna see more than that. So yes, it is able, it has exceeded its nominal design characteristics.
It's nominal design.
We're very happy about that.
Okay, got it. Okay.
Now, obviously, it seems obvious that these could be used to document climate change, like desertification.
Yes, absolutely. And they are being, and these data records, they are very much so being used for these purposes and all kinds of other things. And you can actually see, so if you go to worldview, and I can see if this actually will go to that. I'm not much of a Windows user. I haven't really used Windows since Windows 95. can see, so this is January 2021. So same day, different years. So this is when they had the absolute minimum snowpack, and they were having all these water restrictions and everything.
Is this California?
This is California. This is the Central Valley right here. So Los Angeles is right here. San Francisco is right here. They were having all these water restrictions, drought, all that. So they had some relief from it now. You can see the same month in the winter. So this is winter of 2023. As to clouds. So in 2024. But you can see it's a lot greener, isn't it? So you can play all these games, like you can look at, you can go to, and because this is a global, because, see, we're spoiled, with Tiros 9, somebody sitting there with scissors and a glue stick, gluing those pictures together. We're spoiled brats now. Computer assembles these global pictures of today's weather. Automatically, it updates every time a new piece of data comes down, it updates itself. And so you can actually, if you watch this website for, you come back to that website every couple hours, it updates as the new orbits come in and they're processed and turned into bits and bytes and turned into nice images. You can actually see it updating. And yeah, we're spoiled brats now. These global weather images of Earth's weather are like the norm now. If we don't see it, we're like, oh, what happened? But you can actually see. So I grabbed the. So this is where I grabbed the. So this is the more zoomed out view of the aftermath of our cute little snowstorm we had, and you can see that it has moved off the coast. So you can actually kind of like do like weather analysis. You can see that the storm has moved off the coast into the Atlantic Ocean. What you can also see is who got snow and who didn't. So the snow fell. It's looks like central Ohio didn't get any snow. Of course, Michigan got walloped, and us, like even as far as Missouri, even as far as Missouri looks like got some snow. But then, of course, then it just got too warm and you didn't get none. But then what you can actually see is this right here. When these clouds line up like this, this is a phenomenon called cloud streets. When we see these clouds like that, they tell us that the air that is, and of course we can feel it because it's freezing outside. They had a 2-hour delay at school today. But we know on the ground that it's freezing, but a meteorologist looking at this data who is not here when they see this kind of phenomenon, they can tell that the air that is coming behind this front, that is coming behind all these clouds, is extremely cold. Also, if you look at the direction of these lines, they tell you which way the wind is blowing. And the reason the clouds line up like that, the air that's coming in, the water is still warm. Ocean water has an obscene amount of thermal inertia. It takes forever to cool off. The air is extremely cold. So any water that evaporates from there are a lot of different things you can actually see from just looking at a satellite image like that. These high resolution satellite images, and we can see deserts, we can see dust storms, we can see hurricanes, and you can watch it on a daily basis. Just kind of you can literally watch a hurricane travel across the Atlantic. You don't just going on this website and kind of staring at it.
So basically, if you go to Worldview and want to see what the weather looks like in Garrett County, you don't have to worry about all the pop-up ads on the weather channel and all that.
No, there are no ads. I promise you, there are no ads on U.S. government websites.
No beautiful women from Columbia will love to meet that.
Yeah. And so this is the Nile Delta. Now these dots that you see right in the middle are actually cities. It is extremely densely populated. And those lines connecting them, there's a road. And we can come in and close. And so you can literally spend, so this is something that the U.S. program has, allowed us to do, is develop a new and improved way of wasting time. So, but that's, and so you can, well now you see what the heck are these little circles? Those are center pivot irrigation fields. So that is where they're pumping groundwater, so we can actually see, we see agricultural activity. We see these in the U.S. too. There are a lot of them, especially out west. There are a lot of these center pivot setups where they have a well in the middle. But we can actually we can literally count them and see how much crops is being grown. Moreover, from the really high resolution ones like Landsat, because different plants, we know this naturally. Different plants have different colors. We can actually see that from space. We can tell the difference between corn and soybeans, and wheat, and how close that wheat is to being ready to harvest. We can tell all these things because all these plants, because we know they have different colors, they also have additionally different colors that we cannot see, but we have sensors our eyes cannot see, but we have satellite sensors that are able to detect the reflection in those particular colors. And we can moreover estimate not just what kind of crops are being grown, so this is for agricultural applications, not only what kind of crops are being grown, but what stage of development those crops are, and how soon they're going to be harvested, how well they are doing. So we can tell all these different things from just looking at a few satellite images, and possibly tracking them over time, because we expect them, because they all go through known progressions of development. And we can look at we know what is expected, and we can compare it to what we're observing, and then we can make and there is something there like, it looks like there's some fallow fields right here. It might be continuing. Because some of these circles over here further north are not
You
filled
can
in.
go to a different year and see what.
Yeah, also, sometimes you have to go see 4 or 5 years how the farms may be expanding too.
So on these satellites, those, you see that central line and those evenly spaced.
That is,
Those are the actual geographical,
those are roadways.
those are roads.
Those
okay.
are roads.
So
Yeah, those are roads.
So nothing with like the images being put together.
No,
the satellite being,
no.
That's just actual.
Those are actual, these are actual landscape features.
Okay.
You can come in closer, you can actually see how they kind of, these are, yeah, no, these are actual landscape features. There's much more farming over here too, kind of expanding into the desert. And actually, if we flip the years, we can kind of see how different. We don't have clouds in the way. We can actually see how they change. And so if you kind of sit there and do a few screen grabs here and there, and you can actually see how they change over time. So you can actually see here, that is a new
Right,
development.
yeah.
The roads weren't there.
Yeah.
That's a new development. There you go. In 2016, they weren't there at all. So we come back to 5 years from now, it's gonna look different again. Yeah, they weren't even there in 2016. There you go. It's I'm pretty sure so they put in the roads. It looks like they're expanding the farming sector over there. They must have found water. So the first thing is they put in the roads. They divided it all up. They're probably in the process of installing the equipment for pumping groundwater. Come back to another 5 years, see what they've done with it.
Do you see trends? Is the earth typically more and more crops, more and more green? And would that be more and more carbon frustration?
It depends. Because also it depends on what you do with those crops. Because if you burn after growing, you're putting all the carbon right back where it was. It depends on if you plow stuff over, then you're effectively sequestering carbon. If you burn what's left, well, you just put it right back out where it came from. It really depends. It depends on, we look at such things as forest health. For example, we look at the amount of moisture that's in the soil. We're able to detect that from spacecraft now with the technologies that we now have.
Do you know how many farmers are using these technologies? Like you
Yes,
said,
actually,
California.
Department of Agriculture is one of our biggest customers. There are other federal agencies and local agencies that have subscriptions to this data that is additionally pre-processed so that you can actually go and add layers to different that would be various
So you can
interests.
see how much methane, like a gas plant was
Yeah.
escaping from a gas plant or
Yeah,
whatever.
you can actually see that. If you're interested in that, you can add a.
Well, we have a gas plant in Axel, it's one of the biggest polluters in Maryland, yes.
You might not have the resolution to exactly see the plant,
Right.
but if you zoom in close enough,
In that
you may
area.
notice that something sticks out from the background.
Right.
So yes, you can definitely see things like that. But yeah, we have U.S. Department of Agriculture is one of our biggest customers.
Wow.
As they have
They
six
probably
pages.
use it to track forest fires too.
Absolutely, yes. You can track, we can actually see fires that are actively burning. It is possible to see that, from space. Because the temperature because we have channels on these instruments that can detect temperature. In the channels that measure temperature, active forest fires, well, they light up like birthday candles. You can see them literally from 600 miles away. Without any trouble at all.
What a lot of features. Wow.
There are. I mean, we've had 20 some years to build up this, to build the system up. And it's all public. It's all, it's all there for anybody who's interested. It's all there free for the taking. Well, it's taxpayer dollars. Exactly. So I always tell folks just like how useful a lot of this information is, and all the different ways that you could use it to highlight different things that are, happening, and why they're happening. A lot of the time you can actually make, and even you can, like I gave some examples, like you can actually even go back to history and see why things landed the way they did. Why did Columbus end up landing why did Columbus, leaving Spain, ended up landing in the Caribbean? That is because we can see the trade winds from space. They're very easy, and it's not just Columbus who gets transported. The dust from the Sahara Desert lands in the Bahamas and actually plays a major role in fertilizing the ocean around the Bahamas. That is why you have all the fish, because the ocean itself is extremely nutrient poor. So things that you need for the oceanic plants, the algae, need the same micronutrients, same metals, and same iron, phosphorus, copper, magnesium, that nitrates that are needed by terrestrial plants. They have no way of getting that from the ocean water. So the dust that is being transported from the world's desert actually is the reason we have life in the oceans.
So is that why we see green in the water?
Some of that is sediment being washed from the Nile into some of that is fresh water that is mixing with ocean water. And some of it, and that mixing creates some turbulence, but if you look at, if you look especially in the aftermath of volcanic eruptions, you have a volcanic plume that goes over the ocean, and a few weeks later, you see huge algal blooms in their wake. And so the volcanic ash precipitates into the ocean. Well, ocean water is slightly acidic. It very quickly dissolves into the nutrients necessary for the algae. Then all of a sudden you have these explosions see how much dust is in the air today. Like that kind of thing, you couldn't see that. But it's kind of now, like in the last, this has really taken off in the last
So
10
they
years.
really refined it as they've gone along through the 10 years.
Yeah. Yeah, we continuously refine all these processes. That's part of NASA's mission with the education and outreach. Is we make these systems available so that the general public can actually, because we're in the business of research. Unlike NOAA, we're not really in the business of weather forecasting. And I'm a research meteorologist. I'm not an operational forecaster. I can cut my own weather forecast.
So you are a meteorologist.
But I'm a research meteorologist. So I'm not an operational forecaster. I'm not somebody who writes. I can look at model ensemble. I can look at satellite data. I can cut a pretty decent short-term forecast. But that is not what I do. So the research that I do is basically finding different ways of using the satellite data to get at different physical quantities about the atmosphere. Specifically relating to clouds. So, and their properties. Because actually the contributions of clouds to the Earth's energy balance is one of the major things that I still have in terms of figuring out the climate change factors. That and the aerosols, the various non-cloud stuff that's in the atmosphere, have the biggest error bars in them, have the biggest uncertainties on them, on their contributions. And so so those are actually like the two most active research areas in terms of climate